last time. And so last time we learned about different concentration units. And today we're going to be dealing with solution stoichiometry and serial dilutions, really. That's the big point for today, is the dilution equation and how to make up multiple solutions for an experiment. So I'm trying to focus on those skills that you'll need going forward, either in some other scientific discipline or even further in chemistry. And so this is a really big skill. Diluting solutions is one of the top needs that we have. So let's start with the typical experiment. We're going to weigh out a certain amount of material. So let's make up a copper sulfate stock solution. So if we were doing an experiment that was going to use copper as the analyte, and let's say we were going to analyze drinking water for copper, okay, we would need to figure out how to calibrate our instruments so that they were sensitive to copper. And then we could take water samples. I mean, that's what this university does for TDCJ. They go around to different wells and stuff that they have on their properties, and they send their water samples over here to TRIs. And they have calibrated experiments, and they test those water samples for different metals or other kinds of elements. And so if we weigh out 1 gram of copper sulfate, put it in the beaker, weight it on the balance, how many moles have we got? So this is pretty straightforward calculation of mole conversion. So you look up there on the periodic table, you got 4 oxygens, a sulfur, a copper. You add all of that up and it's 159.6. So I've got the number for you. Okay. Just want you to know where it came from though. And so you divide by that molar mass and you get the number of moles of copper sulfate. Now you do need to check on this isn't in the notes, but you definitely need to check the bottle, because sometimes when you look on the bottle, it'll say copper sulfate hexahydrate. So it's been crystallized with 6 waters around it. And so you got to include those 6 waters in the molar mass. Okay, we're just doing the copper sulfate here, but just always look at the bottle to see what's actually in the bottle. Like calcium citrate, you got to figure out what citrate is, and you got to add that in to the molar mass and so on. So anyway, we've got copper sulfate here, and so this will give us 0.006 moles of copper sulfate. Okay, that's the amount of moles we have in our watch glass or our weighing dish or our beaker. Let's put it in a volume. So let's put this in a 100 ml volumetric flask. So there's an example of a 100 ml volumetric flask. It's a TC, it's to contain. So we would put that copper sulfate in here, this little blue powder down at the bottom. We would add water to about that level, put the stopper on and shake until it's all dissolved. And then very slowly we would dilute that up until the meniscus is at the mark. So the meniscus comes around and hits the bottom of that. The bottom of the meniscus hits that mark. And we would have 100 milliliters plus or minus 0.08 milliliters. So this has, 4 significant figures. So this would be, again, the moles of the solute and liters of solution. So our molarity would be the 0.006 moles of copper sulfate divided by 0.100 liters of solution. Okay. And so this would be our stock solution. So this is our really concentrated copper sulfate. Now, one thing that I'm going to do next is I'm going to show you how we calibrate the instruments, but I'm not really going to get into the instruments or the y-axis on this, okay? But I am going to say that these instruments, if they were sensitive to copper, would give us a certain signal. If we put that solution in here, we would get some signal from our instruments, and that would be the signal from this concentrated solution. And, you could imagine that if you had 0 copper in there, the instrument wouldn't read anything, but that's an assumption. This would be what we call a one-point calibration. So we just have one concentration. We have the signal from that concentration. That's enough to draw a line down to 0. And so if I had half of that signal here, then I could come over here and I could assume that my concentration of my unknown was 0.03, right? But we might be wrong. We really don't know if it goes to zero. There might be some noise in the instrument where it doesn't go to zero signal. It might go to, 1/10 of that signal when you go to 0% copper or zero molar copper. And so we can get other solutions in this range between our stock solution and zero by dilution. We don't have to go back to the balance every time and weigh out more copper. And so that's the main point here, is that we don't want to always have to start at the balance and weigh out our copper. We have a concentrated stock solution, and we could just take some of that and add more water and get one of these weaker concentrations, and then add a little bit more water to a little bit of that and get another weaker concentration. So that's what we mean by dilution. We get other data points on here. And what if our data points looked like that after we measured them on our instrument? Actually, we'd have a better line, and this would be our calibration line, this red line. And notice how it does not go to zero signal with zero concentration. There's some offset here. And so we would fit that to a line, y equals mx plus b, and this b right here is our intercept. It's our y-intercept. When x goes to zero, we end up with b signal. Okay. That's kind of convenient too, because b, that would be what we would get if we had a blank. So if we put a sample of water in there that didn't contain any copper, we would get our blank value, and that b is our blank value. Okay, so that would be the zero concentration of copper signal that we would get. And then we would know, if we got a signal that was half that, if we come over here and where it hits that line, that's actually the concentration of our solution. It's not 0.03. It looks like it might be 0.02 or 0.15 or something like that. And so this line is really important for you to be able to understand how much copper you have in an unknown water sample. So let's work on getting these other concentrations. This is the dilution equation. If I take a volume of a concentrated substance, so I've got a certain molarity, if I take a volume of that molarity and I multiply those, then I end up with the number of moles, right? Volume times moles over volume. So this is say liters, and this is moles per liter, then I get moles. If I take those moles and put them in a new volume, then I get a new molarity. And that's the whole point of dilution. When we take a certain volume of our stock solution and put it in a new flask and add more water, we're taking a certain amount of moles out of our stock solution and putting them in a new volume so we get a new molarity. And so this is the equation that we talk about, the M1V1. M1 stands for the concentration. So the molarity times the volume is equal to the new molarity times the new volume. Very simple equation, but it's the key to dilution. So this is the process of dilution. We have our stock solution that we made. Right here, the 0.06 molar copper sulfate, that's the concentration in our stock solution. And so we're going to call that M1. Now, how can we take a very accurate amount of volume out of here? Well, we have these things called pipettes. And so the larger volume pipettes are these glass pipettes that you can see the marks on here. You have, the 5 mil pipette, 25 mil, 500 mil, or 50 mil and 100 mil pipettes. Typically, you use these with these little rubber bulbs. So you put them in the flask, and you have a rubber bulb that you press against the top, and you pull a vacuum on the pipette, and the liquid pulls up. And then there's a line on here. You can barely see this one. There's a little scratch mark on there so that it's very accurate. So you pull the liquid up above that mark, and you take the bulb off, and you put your thumb over the end to cap the air. And then you slowly drain it down until the meniscus is right at that mark. And then you put it over onto the other flask and drain out the liquid, and you will have delivered 25 mils. So these are TD type volumetric glassware, to deliver. We also have micropipettes, and so you might have seen these. You see these in, what's that? Yeah, and so you see these. We use them in chemistry as well, and so we'll pull up. These are use a little bit of a gas displacement, so there's a plunger in there with an adjustable volume, and so when you pull that up, it might take up 0.1 mil into that pipette, and then you push the air down, and it'll deliver 0.1 mil. So those are micropipettes. And so here's the dilution process. The amount you take out is called an aliquot. So that's a new word for you, perhaps. So that's the amount that's taken out of a stock solution. It's a small sample. So you take an aliquot out of a stock solution that has a concentration M1, and it's placed in a new flask. So we'll take out 50 mils. It's kind of funny. I don't know that they make 50 mil micropipettes. You'd probably have to use one of these down here to get to 50 mils. But anyway, I have it up there by that micropipette. So you take out 50 mils of our stock solution and put it into a new flask, and then you dilute it up to the mark, and then you compute the new concentration. Does everybody understand the dilution process? Take a little bit out of the stock solution, put it in a new flask, dilute to the mark. And so we'll dilute to 100 mils. And so here's our equation. So we solve for M2. So M2 is the original concentration times the ratios of volumes. So we have 0.06 molar solution, and we took out 50 mils and put it in 100 mils. And so you can see that fraction is smaller than 1, so we're diluting that molarity. So 50 mils is on top, 100 mils is on bottom. So 50 into 100, you see that's a 1-to-2 dilution. It should cut it in half. And so you can also use that language. This is a 1-to-2 dilution. 1-to-2 dilution. That's a nice generic way to say it, because that could be 50 into 100. It could also be 5 into 10. If you had a tiny little flask that was 10 mils, you could take 5 mils and put it into 10. That's also a 1-to-2. If you had a liter, you'd have to take 500 milliliters and put it in a liter. And so that'd be a 500 to 1,000. It's also a 1-to-2. And in all those cases, you're cutting the concentration in half.
So only for dilutions, you can use M1, M2 is equal to V1. I mean, M1, V1 is equal to M2, V2.
Yes. Some people have incorrectly learned that you can use that for titrations, but you can't. You can get lucky. You can get lucky sometimes, and it'll work, but it's unreliable. If you have a polyprotic titration, then it'll give you the wrong answer. So, yeah. And so then the result is 0.03 molar. So, yeah, it cuts it in half, as you might imagine. And so on our little chart up here, that would be halfway to 0 would be 0.03. Now, we don't know what the signal is, so I just put that dot up there. So if you're wondering how I knew how high it was, I just made that up. Okay, I'm just really showing you the x-axis. So this is Gen Chem 2, we're just working on the x-axis. When you get to quant, you'll do the y-axis. Okay, and there may be a lab where you do Beer's Law. I have to go back and look to see. But this will get you to understand how you make up your concentrations. Okay, that's the 2-point calibration. So we could have, done our line, our y equals mx plus b, and drawn a line through there. That's a crummy line because with 2 points, it defines a line. So it would be a perfect line through 2 points. But we could stop there, but we'll get better statistics if we do another dilution. So let's do another dilution, another 1-to-2 dilution. So we'll go from 0.03 to 0.015. So let's do that one now. So out of this diluted solution, we take 50 mils out. So that's why it's called serial dilutions. So they're in series. So this is the big word right here, serial dilutions. It's not like breakfast cereal, okay? It's like cereal, like a series, okay? So we took stock solution, made a dilute solution. Then we use the dilute solution like we use the stock solution. So we start with the dilute solution and make a more dilute solution. And that's what the serial part is. It's a series of dilutions. So an aliquot is taken out of the diluted solution, placed in a new flask, and diluted even more. So that's the serial part, okay? And so we've got, again, a 1 to 2, but this time the original is 0.03 molar copper sulfate. And we're going to do a 50 to 100 or 1 to 2 dilution, so that should cut it in half, and we end up with a concentration of 0.015. So then we go down another halfway to 0, and we get a 0.015 molar solution. So you can imagine you can cover a lot of ground with 2 or 3 dilutions, and now you've got a wide range of concentrations, and you'll understand how that instrument behaves at different concentrations. Just so you know, like if you had lots of data points here, and so your line's going up here, but then sometimes the instruments just can't measure anything more concentrated than this, and so then your really concentrated solutions might all have the same value. And so this right here is bad. This is called, the instrument is saturated here. And so up here, this is a bad part of your calibration. So you can't use this for calibration. When the instrument is saturated, notice I'm changing the copper concentration, but my signal's not changing. So I can't really say anything about my copper concentration. What you want to be here is, this is nice. This is a nice linear range of my calibration.
So that's if you just keep diluting it.
Yeah, and so if you had a really strong concentration, let's say we did a couple of dilutions and our signals didn't go down, eventually we'd get down to where they start going down. And when they start going down, then you know you're in the linear range, and that's the range where your instrument is behaving well and giving you good information about the change in copper concentration. You need a slope that's not 0. A 0 slope gives you garbage numbers. You need a slope. In fact, the steeper the slope, the better, because a tiny concentration change gives you a huge change in signal. So that's when again, I'm going way afield, but when you get into quant and instrumental, the steeper the slope, the more sensitive the instrument, because a tiny little change on the x-axis gives you a huge change in signal. So that's great. So again, today we're just focusing on the x-axis and how we come up with our stock solutions. Okay, let's practice. This is another kind of calculation. Instead of just doing a dilution and figuring out what the new concentration is, now we're given 2 concentrations and we need to figure out what the aliquot will be. This is not in your notes, it's just a practice problem. So you can flip the page over if you want, or find some blank space. So you have a big bottle of 18 molar HCl, which is what we buy from the companies, you know. And so this is concentrated HCl. Very dangerous solutions, corrosive to skin. You can see that right here. This little symbol means it's corrosive to skin. You can see the little hand is smoking when it falls on the hand. Okay, and so you want to be careful. Gloves, goggles, the whole bit. And we want to make up something that's not so dangerous, something that's less concentrated for use in lab for our Gen Chem 2 students, so they don't kill themselves in lab. Okay, so we want to make a 0.1 molar solution. And we want to make a liter of that because that should work for a lab section, whatever they're doing. Okay, so now we have the V2, we have a liter. We have the M2, we want a 0.1 molar solution, and we have the M1, which is out of the bottle, 18 molar. So we need to figure out what V1 will be, the aliquot volume. How much do I take out of the concentrated bottle and dilute to 1 liter? So, yeah. So this we just rearrange, solve for V1, we end up with 0.0056 liters, or 5.6 milliliters. So that's a nice measurable volume. It's kind of hard to pour that out of a big bottle. So just for practice, if you're ever in a stock room and you're making these things up, pour a little bit into a beaker, because a beaker has a big wide mouth, and then use the beaker to pour into a grad cylinder. So this is the glassware that we would need. We need a graduated cylinder, and we need our 1 liter volumetric. And so we would put 5.6 mils into this grad cylinder, probably using a beaker as an intermediate container. And then we would we would put that into the grad cylinder until it reaches 5.6. Now this is it's like a 10 mil grad cylinder. It's not the most accurate piece of glassware we have, but it's better than a 100 mil grad cylinder. And you see the markings. I have 4 and I have 6. What happened to 5? Well, 5 is right here. And I've got 4 tick marks in between. So that means this is 5.2, 5.4, 5.6, 5.8, 6. Okay, so I'm going to go to that line right there, and that's my 5.6 milliliters. And then I'm going to take that and put that into the volumetric flask with water. So I'm going to have water in here first, a little bit of water in here first, then drop in the acid. So remember, do as you oughta, add acid to water. So you put the acid in to the water, and then you dilute to the mark, which is right there. Okay, you let it come back to room temperature, it'll warm up, you swirl, so it's well mixed, dilute to the mark, and you're good. So you've made up your 0.1 molar solution, and now the freshman chemistry lab can operate safely instead of using 18 molar HCl. This stuff is so strong, you open the bottle, your eyes start burning. It's giving off so much HCl that it just is really hard to work with because it's so strong. Okay, here's some other tricky concentration problems. Just from the past, I know the students, whenever they hit these on the homeworks, always come up after class or whatever and ask, I don't understand this problem. So when complicated electrolytes dissolve in water, and that's things that have subscripts like Na2SO4, right? That's more complicated than just NaCl. Okay, 1 mole of NaCl gives you 1 mole of sodium ions and 1 mole of chloride ions. But 1 mole of Na2SO4, sodium sulfate, gives you 2 moles of sodium ions. And so what's the molarity of sodium ions in a 0.1 molar Na2SO4 sodium sulfate solution? So it's very simple. You just take that formula there, and it's Na2SO4, and you make a mole ratio with it. So for every mole of the sodium sulfate you have, you end up with 2 moles of sodium in solution. So this is 0.2 molar sodium sulfate. Okay. Any questions on that one? Okay, let's practice on one that's also just, well, I see you're writing. Let you finish writing. Okay, let's practice on one. So I'll put in another problem here. It's not in the notes. So what's the molarity of sodium ions if 10 grams of trisodium phosphate is dissolved in 1 liter of water? This is a really good cleaner, and this is a very cheap version of it. You can buy really expensive cleaners for, what am I trying to say, for like glassware and so on. And it's essentially trisodium phosphate. So you can buy this straight up, super cheap at Home Depot. So let's take, we need to know the molar mass. We have 10 grams of trisodium phosphate. So that's trisodium, so Na3PO4. So help me out with the molar masses. I have 4 times 16. What is that? 64. And then I have a phosphorus. Where's phosphorus? I can't read that from here. Can you read that? What? 30.9? We'll go with 31. Okay, 31. So these are all grams per mole. Okay, and then 3 sodiums. Can you help me? Let's see, I can see that one. 23. Okay, so that's 69. Is that right? Check my math because I don't want to make mistakes. Okay, 9 and 1 is 10, 4 is 14. Okay, 6 and 6 is 12, 13, 14, 15, 16. Did I do that right? Okay, thank you. Okay. And I'll just do 0.061. And then what we're interested in is the sodium ions. So 1 mole of Na3PO4 gives 3 moles of sodium ions. So 0.18. Okay. And then this is divided by 1 liter. So that's the molarity. So it's 0.061 molar sodium phosphate. It's 0.18 molar sodium ions. Okay. Any questions on that? Pretty straightforward.
There'll be more practice problems.
Yeah. So we'll put some on the homework. Now let's just go through some of the different solution facts and so on that we have about the course. What? This is just, again, some concepts now. We're done with the calculations for the day, so we'll go through some of the concepts, and we're going to finish a little bit early because I have a luncheon that I have to go to. The president's given a nice luncheon for the faculty senate, so I'm going to go have lunch with the president, so that'll be cool. So generally the solubility of solid solutes, so these are all salts that are soluble in water. These would be their saturation points, and so this would be the maximum amount of these salts that you can put in water given a temperature. Okay, so you could put, sodium chloride at room temperature, which is 25 degrees. You could put about 35 grams of salt in 100 grams of water. It's pretty concentrated. It's like 25% salt in there, so very concentrated. If you warm that solution up, it would go up, right? But it wouldn't go up that much. Look at potassium nitrate. You can put about the same amount of potassium nitrate in water at room temperature, but if you just warmed it up a little bit more, look at it, it's 100%. You can put 100 grams of potassium nitrate in 100 grams of water at 55 degrees C. But the point is, generally, the solubility of solid solutes in liquid increases with increasing temperature. I do not know what's going on with the cerium sulfate. So, that's kind of weird, right? So that's why it says generally, right? So out of all of the ones shown on here, we would be wrong for cerium sulfate, but we would be right for all the others. Okay, so in general, temperature increases the solubility of solids in liquids. Okay, the opposite is true for gases. So if you raise the temperature, the gases leave. So carbonated drinks are more bubbly. If you store them in the fridge, it holds on to that CO2. You warm it up, it goes flat. We've seen that. You leave a Coke out, and all of a sudden it tastes awful. Warm lakes have less oxygen dissolved in them than cool lakes, but warmer lakes have probably a higher activity of algae, and so then that generates more oxygen. So lakes are very complicated. So this is kind of a simplistic statement, I think, in the notes. There's other kinds of things. This is strange behavior, this classification of properties called colligative properties. And so when you dissolve things in water, the properties of that solution change. We looked at the phase diagram for water, and we saw the vapor liquid line, which is the vapor pressure line, and the freezing line. And when you add salt into water, it changes the properties a little bit. And so what happens is it will lower the vapor pressure, which means the boiling point goes up. So it'll boil at a higher temperature. So you put a little salt in there, you can get the temperature to boil a little bit higher. And some people say, well, you put a little salt in there, your pasta will get done faster. But it will raise the temperature a little bit, but probably not so much. I think it's more just a urban legend. I don't know what else to call it. It will also depress the freezing point, and then this colligative properties are related to osmotic pressure. So let's go through these different properties. Here's that PT phase diagram, and you can see the pure liquid line. So this is the pure liquid solvent line right here. And then you add salt, and look how that line moves. It moves out a little bit. And so if you come up here to 1 atmosphere, the boiling point has gone up. So see, we have an elevation of the boiling point because this line has moved up. So what that means, I mean, it's just made the entropy of the liquid more higher. And so then that's what moves these lines. And so the boiling point goes up, so we call this boiling point elevation. And notice also that the freezing point has gone down. And so this is freezing point depression and boiling point elevation. So it's kind of strange. You add a solute in water and you get a wider range of the liquid. It melts sooner, like at a lower temperature, and it boils at a higher temperature. So it makes the liquid more stable. This also makes sense in terms of the boiling point because you've got ions in solution now, and that is more intermolecular attractions. And the more intermolecular attractions you have, the higher the boiling point. These are really simple equations. It's a linear equation. This boiling point elevation constant here is multiplied by the molality. And that's the one place where I've seen molality used. These are the actual practical applications of that. So in the wintertime on bridges, they'll throw down something that's water soluble. And so when it rains and then the cold air comes along and tries to freeze that rain, make a sheet of ice on the bridge, this colligative property, this stuff that's dissolved in water, will make the freezing point lower. And so if the air temperature doesn't get low enough, it won't freeze, and that'll keep the bridges from freezing. The same with the wings on your aircraft. The aircraft have to go through a really moist zone before they get up to cruising altitude. And in that moist zone, on the vacuum side of the wing, on the top of the wing, water can form ice in that lower pressure region, and it'll ice the wing. And so it'll change the shape of the wing and add weight to the plane. And so the plane gains weight and loses lift. Those are two very bad things when you're trying to reach altitude. You start to lose lift, and the wing shape is changed, and planes can crash. And so on the way to takeoff, you go by this de-icing station, and they spray this like antifreeze type solution on the wings that sticks to the metal and allows them to get through the clouds where ice would form. And they get above that where it's dry, and then they're okay. It's really cold temperature up above those clouds, but there's no moisture. They just have to get through the moisture zone so that they can cruise. Yeah. The colligative properties of electrolytes, if you have a strong electrolyte like a salt, you're going to get more particles. So the colligative properties, that freezing point depression goes up as the concentration of the particles goes up. And so ionic substances, electrolytes, will give you more particles than something that's also soluble in water, like methanol, but it doesn't give you ions. It will still lower the freezing point, but not as much as the equivalent mass of sodium chloride or something like that. This saved me one time. Going back home to Dallas-Fort Worth from college, got to around Waco, and an ice storm came through, and my windshield was icing up. And my defroster would only defrost like a little circle right above it. So I'm driving down 935 looking through this hole, and I pulled off. I think it was in Troy. There was a little convenience store there, and people were asking for de-icing solution, and the guy said, "We're all out." And I said, "Do you have any rubbing alcohol?" And the guy said, yeah. And I went and grabbed some, and everybody in the store was like, well, that worked too. So I'm a chemistry major. I was like, yes, it will work. Anything soluble in water will work. So I went out there and dumped it all over my windshield and got on the road and tried to get going. Oh yeah, they were like grabbing it off the shelves. It was really great. Yeah, it had to be pretty concentrated IPA, but it was. They had like the 90%. It was good. Yeah. So then osmosis, this is kind of an interesting phenomenon. So anytime you have solutions in contact with each other and you have a little barrier like a membrane, they want to achieve the same concentration, right? And so if that barrier won't let your solutes through to one side, then water will flow through to try to dilute those solutes. And so here's a picture of that. If we zoom in, so here on this side, we have a concentrated solution on this side. And so water's flowing through to try to dilute this side so that they come to equilibrium. And so water's flowing through that semi-permeable membrane. And what that does is that pushes more volume over here. And so you could look at this difference, and that's what we call osmotic pressure. So this column of water that grows on the concentrated side is a way to measure this osmosis effect, this osmotic pressure. Remember, it's related to the number of particles. I would say proportional to the number of particles. That is cool, okay? If I've got an enzyme that's soluble in water and I could purify it, I don't know its molar mass, but I know its mass. So I put that in the water on one side, put pure water on the other, and it grows on the enzyme side, and it's proportional to the number of enzyme particles I have in there. So this is how I can measure molar mass. This is counting, which is moles. Okay, lunchtime. And so this is how I get molar masses of things, polymers, enzymes, and things like that. So typically large things that won't go through the membrane, I can put them on one side and let water try to dilute them, and water's kind of giving me a count. I weighed out 100 grams, and it grows, and it says, this is fictitious, but there's 2 particles in there. Then I know each particle weighs 50 grams, the molar mass, right? And so that's an extremely ridiculous example. But the point is, it grows by the number of particles, and I know how much mass I put in there, so I can get the molar mass. I can run this backwards to purify water, and that's what reverse osmosis is. So I have a salty solution over here. If I push on this side, I get pure water on the other side. And so that's a nice thing. And then this happens every day in our cells. If we tried to drink salt water, we would get a hypertonic solution in our bloodstream, and our cells, red blood cells and so on, would shrink, and that's called crenation. Here's a little picture of the crenated cells. They're like real leafy looking. And then if I have it in deionized water, it's not good to drink deionized water because then your cells will swell and burst. And so you can have extreme situations with hypotonic and hypertonic solutions. Okay, and then the colloids are just suspensions of particles that are too small to be settled out by gravity. Things like fog, smoke, and foams too. Some of these are solid. So the rest of the notes, that's pretty much it. So thanks for letting me finish early, and I'll see you next time.